Welcome back. So now let's continue with the FreeRTOS configuration. Let's start with the SystemCoreClock variable. This variable should reflect the actual CPU clock speed of our system, and FreeRTOS uses this value assigned to config CPU clock hertz to make accurate timing calculations. We need to ensure that SystemCoreClock is correctly updated to match the CPU's operating frequency. We can utilize the system STM32F4 XX.c file, which is designed to set up the system clock at startup. cubeide may not generate this file automatically, but we'll bring it into the project from the STM32 software package. But first, we'll take a look at the header file for it right here. So let's go ahead and review this briefly. And if we scroll down a bit, here we have the SystemCoreClock variable again, where the comments mention that this variable is updated in 3 ways. And we'll use the first method mentioned, which involves calling SystemCoreClockUpdate from the system.c file. And again, the cubeide didn't provide us with the system.c file, so we're going to import one from the STM32Cube firmware package. Alright, so let's head over to the software folder. And let's navigate back to the main folder right here. And let's go to Projects. Then we want STM32F446E-Nucleo. So let's go inside, then go to Examples, then RCC, and we can take the file from this example here, and it's under the source folder. And here is our system STM32F4XX.c file, and we can simply drag this file over to the core source folder. So go ahead and select it, and drag it over, and copy files. All right, so let's take a look at the file. And scroll down a bit to find the SystemCoreClock variable. And here we can see that it's initialized to the default clock speed of 16 MHz. And we have the same comment we saw from the header file. So let's go down a bit further to see where it's updated. And here we have the comments for the SystemCoreClockUpdate function. So when we initialize the clock, and of course prior to starting the OS, we'll call this function to be sure that the SystemCoreClock variable is updated, as FreeRTOS relies on the SysTick for its timing. So now that we understand the importance of keeping this variable up to date, let's go back to the FreeRTOSConfig.h and take a look at some of our basic configuration options. Alright, so I'll just run through these pretty quickly. The first 2 here are related to the CMSys version, so we could leave those commented out, as we're not using the CMSys layer above FreeRTOS. And config use preemption allows us to use preemptive scheduling, and that is what we want. And we won't implement hook functions. And 7 different priority levels should be enough for now. We could always adjust it later. And we won't use static allocation, so these are all okay as is. Then we have our clock, which is assigned to the config clock hertz definition. And then the tick rate is 1 kHz, which is typically the default, so that's okay. And this means that the SysTick timer issues an interrupt every 1 millisecond, and the minimal stack size is okay, and we can leave our heap size as is for now. So these all look good. So moving on, we'll definitely want to use mutexes to protect our Modbus buffers, which we'll see later in the course, and we won't check for stack overflow, and the rest look good for now. But we do want to add another definition here, so let's add a define for config record stack high address and set it to 1. And this option is incredibly useful for debugging, as it allows you to track the maximum stack usage for each task. And just to show you quickly, this is actually used in tasks.c. So by enabling it, you're effectively monitoring each task's stack usage, which helps with detecting potential overflows and improving overall application stability. We'll come back to this later in the course when we complete the stack monitoring setup. And next, we'll also enable generate runtime stats by setting it to 1. This feature provides valuable insights into task runtimes and helps in fine-tuning task priorities and analyzing system performance. And again, we'll complete the runtime stats setup towards the end of the course, as there is more to it than simply enabling this option. We would also need to create a function to set up the required timer, and another to get the runtime counter value. So without those functions set up, enabling this option will result in a build error. But that's okay, as I'd like to highlight that sometimes enabling one option without its prerequisites results in unexpected issues. Alright, so now let's move on to the next set of options. The coroutine definitions we can leave as is, and the software timer section looks okay. We actually won't use timers. But in the next section, let's set include vtask delay until to 1. This option is useful for creating tasks that execute at precise intervals, ensuring consistent timing for periodic activities. Alright, now let's scroll down a bit, and we could leave this section alone, as these definitions are related to the CMSys layer, which again we're not using, but they're here in the case that you ever need them. Okay, moving on farther down the file, and we encounter the Cortex-M specific definitions. Here, config priority bits is set using NVIC priority bits. Since NVIC priority bits is defined as 4, this means that we have 16 priority levels available from 0 to 15, because the number of priority levels is calculated as 2 to the power of the number of priority bits. And the next two definitions are important for us when setting the priority level of interrupt service routines that use FreeRTOS APIs. As you may already be aware, in FreeRTOS, priority levels are defined inversely compared to Cortex-M Core standard priority levels, where a higher numeric value represents a lower priority. The config library lowest interrupt priority is set to hex F, or 15, which is the lowest priority for interrupts in FreeRTOS terms. Conversely, config library max syscall interrupt priority is set to 5, so we'll ensure that our ISR priorities, which require the use of FreeRTOS APIs, like semaphore give from ISR and so on, are between 5 and 15, so that we adhere to these configurations. And the next two definitions are used by the kernel itself, and they are generic to all Cortex-M ports. They standardize how the FreeRTOS kernel interacts with the EMCU's NVIC priority levels. Okay, and then we have config assert, which is like a normal assert without relying on the provision of the assert.h header file. And lastly, for the core FreeRTOS handlers, we have the SVC handler, pinned SV handler, and the SysTick handler. These handlers are defined to match the standard Cortex-M handlers within the FreeRTOS port file, port.c. Specifically, the SVC handler initializes the RTOS scheduler, the pinned SV handler is responsible for performing context switches when needed, and the SysTick handler increments the RTOS tick count at a frequency set by config tick rate hertz, which in turn can trigger task switches. And if you recall, we have config tick rate hertz set to 1000 at the top of the file here. Alright, so that's all for the slight configuration adjustment and overview. So let's continue in the next lesson by creating the startup task. See you there.